You got 20 minutes max. I'll give you when you have about 5 minutes left if you go that long.
Okay, thanks. Hi, everyone. I'm Brian. I'm doing my presentation on 5G smartphone antenna design. I picked this topic because I didn't know anything about 5G and I just thought it was cool, so I thought I'd check it out. In this presentation, I'll go over a 5G overview of specifically for smartphones, just so we have a better understanding of how the antenna design works and why it's designed that way. And then I'll talk about the IEEE paper's design that I chose, which operates at 3.5 gigahertz and 28 gigahertz. So following that, I'll show you guys my FICO simulations and compare the results. And I'll end with some future improvements if I had more time, like what I'd work on. So to begin, what even is 5G? Basically, it's just the 5th generation of technology for wireless communication. And there's a lot to it, but I really only want to talk about 2 main features, which is the high data rate and the enhanced capacity for multiple devices. Yeah, so I stole this graphic. I borrowed this graphic off of Google Images. And I just thought it was really interesting comparing the generations of cell phone. Yeah, we have this graphic from like analog signals, analog communication, all the way to 5G. And we can see that from generation to generation, there's a large increase in just data rate transfer and like the capabilities that we can do with it. And I think this graphic down here is really interesting because from 4G to 5G, it goes from jumping over a hurdle to riding a rocket, which I don't think is really accurate, but some of the reasons for that would be just the operating frequencies of 5G. I think it can depend on what frequency you're operating at, which will give you higher data rates. So 5G consists of a low band, a mid band, and a high band. And this high band is more known as the millimeter wave frequencies. So T-Mobile is currently like the leading provider of 5G, and it operates at these 4 frequency bands of a low band of 600 megahertz, the mid band of 2.5 gigahertz, and these upper millimeter wave frequencies. But even though it's the leading provider of 5G, like these low bands, they're pretty much just replacing the 4G LTE here, which is, so these high frequencies are more for urban areas. And the reason for that is because there's a wave propagation challenge that comes with using higher frequencies. This is a graph that I got from the 578 textbook, which is showing attenuation versus frequency. So in the atmosphere, attenuation versus frequency in the atmosphere, because there's no free space in real life. And basically what I really wanted to show was this increase in attenuation versus frequency. So 5G, we're really only looking at this segment, but even at those millimeter waves, it's still much more attenuation than at those low bands. And this is what allows us to communicate really far using that low band 5G versus the millimeter wave. So to give a visualization of what I'm talking about is in a city, there's like 5G millimeter wave towers located in the center because they want to supply that 5G to as many people as possible. But as you get further away, you have to start using sub 6 gigahertz, so that mid band or low band. And something that we do to kind of combat this this propagation challenge is by using multiple input, multiple output antenna structures. So basically what this is, MIMO, is if you have multiple transmitters they each act independently from one another, and same on the receiver side. So if I wanted to communicate to different receivers, I could send out, or the transmitters can independently transmit, is what I'm trying to say. So multiple input on the receive side and multiple output on the transmit side. So what's really interesting is we can group up elements in an array fashion and direct the beam. So we get like a more direct, a more narrow beam width. And we can add some phase shift to that to kind of steer the beam in the direction that we want to point it. And these 5G antenna, like the towers, can do this to kind of pinpoint receivers. But MIMO isn't like exclusive to the 5G towers. Like you can also do it with your cell phone antennas. And that's kind of like what the hype is for the smartphone design. Most of these 5G smartphones have at least 8 antenna elements. So if I were to like cover up my phone, some of the antennas with my hand, there's still other antenna elements radiating. So that's pretty cool, which leads me to my IEEE journal's paper design. Basically, it's just a bunch of patch antennas operating at 3.5 gigahertz and 28 gigahertz. And I'll get into a little bit later on how they operate at these two different frequencies. But there's also a second configuration, which is, I'll also show the differences between these two. So basically the antenna element is a meandered patch or a patch antenna with an RF switch that connects to a meandered patch. And this is the schematic for the RF switch. And this is the back of our antenna. So we have our substrate and our ground plane. So when we have this RF switch on, then the current distribution radiates throughout the entire patch. And this additional patch like causes our antenna to radiate at that desired frequency of 3.5 gigahertz. When we turn this RF switch off, then only the initial patch antenna radiates, which gives us our 28 gigahertz desired frequency. So this is configuration A. There's a lot going on here, but pretty much the only thing we should take a look at to take note of is the S11 parameter value. So the peak value of the reflection coefficient is a little bit less than minus 21 dB, or greater than, however you want to think of it. And then this is the actual data, which is like, it's better than what they simulated, but which is a little bit weird. Moving on to configuration B, we have something similar. Again, configuration B is the antennas are on the long side rather than the short side. But if we look at 3.5 gigahertz, we see a multitude of different values, and that's because the spacing of the antenna elements are like the wavelength that corresponds to 3.5 gigahertz is much larger than for 28 gigahertz. But again, with the actual results, they're pretty good results. I'd like to note that the dB is around minus 25 for each of these. So the operational frequency gain, again, there's a decent bit going on here. So configuration A is the dotted lines for both of these graphs, and configuration B is the straight lines. And both of these configurations perform pretty similarly. But for 3.5 gigahertz, we notice that the gain is much lower than for 28 gigahertz, but the efficiency is higher than for 28 gigahertz. And I think that this is okay because of the reason, because like the 28 gigahertz propagates, it doesn't propagate as far as the 3.5 gigahertz. So I think that's why like they're cool with this design, I guess. So my FICO simulations. First, I'll talk about the single elements that I simulated, and then I'll talk about the antenna arrays of configuration A versus configuration B. And then I also simulated like additional substrate interference and the effects of additional material. So this is my 28 gigahertz element. I use copper as the material for my patch, and I made like an edge port over here. So this is the 3D radiation pattern, the S11 parameter, or the reflection coefficient. The first thing I noticed was that it wasn't exactly at 28 gigahertz. And I think this is because the dimensions were incorrect. Like I could have optimized it, but I wanted to follow it. I wanted to follow like the specified dimensions given by the paper. So the second thing I noticed was that this reflection coefficient was -60, which is like freaking amazing. So that was really awesome. And the gain is around a peak gain of like 6.5 dB, which is also a little bit less than what the paper simulated. For the 3.5 gigahertz, notice that I didn't make an actual RF switch. I just used the microstrip and attached the meandered patch. But yeah, as expected, the gain is a lot lower. But this is the 3D radiation pattern. And for the S11 parameter, the reflection coefficient results were much worse than what the paper had. And I think this might be because of the RF switch, but it might be for other reasons as well, which I'll get into after I'm done showing the simulations. But for the gain, again, this is kind of expected to see that drop in gain from the 28 patch or 28 gigahertz patch to the 3.5. So this is showing the surface current. Shout out to Mark for showing me how to simulate this in FICO. And basically you can see the current distribution for the 3.5 gigahertz is really concentrated at the same spot as in the paper. And obviously for the 28 gigahertz, it doesn't have anywhere to go. So that is pretty similar too. Next, I'm gonna show the configuration A versus B. So this is my 8-element array. I didn't simulate the phone material. I just put the antennas in their positions because it was taking a really long time to solve, and I didn't want to be stuck on that all day. So this is configuration A versus configuration B. And it's cool to note that like as we implement more elements, then the gain of our system or of our antenna goes up. So here's the S11 parameter for the 28 gigahertz configuration A. The reflection coefficient has like the operational frequency has slid down dramatically, but I didn't simulate it again. And I tried doing 4 elements only, and it gives a much better reflection coefficient. So I think that the problem was when I translated it and mirrored it. When I mirrored my 4-element array, I think that the size didn't correspond to the right wavelength, or I think it had something to do with like the mirroring is what I'm trying to say. But if you were paying really close attention, then you'd notice that like when I simulated 1 element, the reflection or the operational frequency was around 2.7. It's dropped down about 1 gigahertz, and that's because, oh, that's not 1 gigahertz, half a gigahertz, 500 megahertz. And that's because of, I used only 11 desired frequency points just because it was taking like a really long time. I didn't, yeah, I just wanted the results. But yeah, the S11 for the 28 gigahertz configuration B, it shows kind of what I expected. So that was cool. For 3.5 gigahertz, they had pretty similar gains, and the radiation patterns are shown below. So this is the S11. Notice that there's this 10 dB reflection coefficient, which I didn't actually think was possible. So I think this is just a simulation error. If anyone knows what's going on, please let me know after after my presentation. But I tried it with 4 elements only, and there is still some like shady business going on at this 3.1 gigahertz. But besides that, this is like a pretty desirable reflection coefficient, I think. So
Okay, you got about 5 minutes there, Brian.
all right, thanks a lot. For the configuration B, this was pretty similar to the single element. So yeah. The last thing I did was the phone material. In the paper, they used the phone material as the substrate. So I just did like this chunk of area with the antenna to see if there is any like impact on the results of the radiation. So this is what I originally did of a single element, and then this is with the additional substrate. So the radiation pattern changes, but not too much difference in total gain, I guess. But here are the reflection coefficients. Again, I think it's because I used 11 frequency points rather than like a continuous frequency solution sweep. Here it is for the 3.5 gigahertz. See a slight drop in gain, and our reflection coefficient value is slightly worse than without like the phone material, the substrate material. So some possible causes for discrepancies would include incorrect dimensions given in the paper, like this 1 plus 2.5 didn't add up to the numbers that were totaled in the bottom here. Also in the paper, they used HFSS instead of FICO. And the number of simulated frequency points that I used, I think this might have been one of the biggest contributors to why I had different values. Just because I more wanted like the results rather than like a really fine sweep of frequencies. Mesh size also plays a role in that. I did a coarse mesh. Maybe they did like fine or standard or something. And last thing could have been like the solver settings. So I use good old method of moments to solve my antenna designs. So yeah, some future improvements include, like if I had more time to work on this, then I would totally optimize my antenna designs for that desired 3.5 gigahertz or 28 gigahertz. Something else I would do is I would create a layered dielectric to accurately model my phone material, because phones are made up of a bunch of different materials, and if I like took the percentage of each of them and like layered them on top, I think it'd give me like more accurate results, or more realistic results, I should say. Something else I would do is explore beamforming capabilities. So I would just like add a phase shift within my array of elements in my smartphone design. And then the last thing I would do would be simulate isolation between elements. So in 5G, it's pretty important to make sure there's like good isolation between element to element so that there's not any unwanted interference. So in conclusion, I hope you guys were able to learn a little bit about 5G and the role that like massive MIMO plays into all of this, and why MIMO is like so important right now. And I hope that it was a good time looking at my FICO simulations. So I'd like to thank Professor Breakall for giving me the opportunity to present at this highly established conference. And if it's the same to you guys, then I'd like to open up the floor for questions.
Okay, well, thank you very much. And we give our applause here, our virtual applause from everybody. I'm sure I'm doing it for everybody. Yes. Oh, there we go. We got some other applause coming in. I didn't know you could do it without the video on. Yeah, there we go. Okay, so we have some time. Do we have any questions or comments from the audience? And wow, you're getting a lot of applause.
Hi.
Oh, thank you.
Yeah, go ahead, Mead.
I got a couple. First, did you have a link to that paper you could drop or email? Do we get a copy of the presentation?
Yeah, you can take.
Yeah, I want to know what
I'll send you
awful
guys a
people
copy.
use 3.5 gigahertz as their center frequency for their experiments instead of like 3.6.
Sorry, what was that?
I want to know like what awful people decided to pick 3.5 instead of 3.6. They're kicking hams off of 3.5 and pushing us down, and academia supporting common number choices and then saying, well, we already have done the work for this is mean. Second point was you mentioned a lot about the higher frequencies get higher gains. You remember last semester we talked about aperture antennas and how when you talk about an aperture antenna, you start thinking just in terms of area, and then you think about the free transmission equation. So for the patch antennas, which behave almost analogous to an aperture kind of antenna, way easier to get higher gains for these higher frequencies, just like a dish antenna, but your free space loss goes down with that. The concern of 28 gigahertz propagates less in atmosphere as compared to 3.5 gigahertz is not so much an antenna gain concern and more so a free space loss. And then the free space loss is, it comes out in the equations, but for the propagation from point to point, atmospheric attenuation worse at the 28 gigahertz. So that's independent of that discussion. You asked about your arrays and getting that higher return loss. Can you go back to that slide?
Yeah, sure.
Did you, that was on the one when you were simulating what, 4 of them?
No, this was my, oh yeah. It started with the 4 simulations.
Okay, so there's four of these and you're stimulating all 4 of them at the same time. I mean,
what do you mean?
The hunch that I have is that you have coupling between them, and somehow it managed to believe that when it puts in a certain amount of power to all of them, it gets more power out at 3 of them than the other one. But it's weird because like they're 10 dB higher and the one of them is 3 dB down. My best guess is because you have multiple, you have coupling between them, which is causing it to look that way, but it's still, that shouldn't really happen. I'm not sure where that.
That kind of went through my head too, and I'm not really sure how to answer your question, but I'd love to talk about it more after class or something, if you're available.
Yeah, I also have never seen a reflection coefficient go up like that. It'd be interesting to look at the actual impedance and see if you have. The only thing I could think is that sometimes in arrays you can get a basically a negative impedance, a negative real part, and it means instead of power coming out of the antenna, power is going back in. Okay, and it does happen sometimes in arrays. I don't know. It seems like the spacing though should be wide enough here. That's usually with real close spacing, but yeah, I agree that plus 10 dB reflection coefficient, it'd be interesting to see what the impedances actually were if you had a negative real impedance there. Any other questions? Comments? It's good if the class asks, then I don't have to ask, but I'll ask a couple, and then maybe you can think there are some questions. For the substrate, did they give the or did you look up the values for what to put in for the media?
Yeah, sure. It was actually given in the paper. I think it was 2.2 for the relative permittivity and 0.0. I'll just check.
Yeah, I guess did it give the loss tangent at each of the frequencies?
The loss tangent was 0.0009, but it didn't give a specific frequency.
Is that at both? Did they say that was at both frequencies, or did they give a frequency?
Specify.
Oh, they didn't specify. Yeah, I would think that the loss tangent would vary with frequency, maybe even the permittivity, but that could be one thing you might want to look into, is actually try to go and look it up, you know, from the manufacturer sometime. to see what's going on there. The other thing, if you look at this, when you showed the currents there, this is actually a perfect slide. I don't understand why you would have all that extra metal up at the top where it said on the left there, it says meander patch, when it doesn't look like there's any currents ever go on that. And it's just sort of curious why they would, it seems like they could have ended the patch right there and saved a lot of metal. I'm not sure why all the metal's there, because it's certainly there's no current on it. So I'm not sure what that metal is doing exactly.
Right.
Seems like they could have just kept meandering the patch.
Did you animate the current in time, or did you only get one screen cap?
Well, no, I only got a screen capture, unfortunately.
Right. I assume that current though that they're showing there, that's the current in the frequency domain, the magnitude, right, at that frequency.
Yeah.
And of course, you're also showing, now you're showing there is some current there, but I assume I'm trying to read it there. I think it is in dB, right? So the top is like, well, on your scale on the left, you sort of, yeah. So you're at 35 or something there, and so the green is down, some 35 dB from what it is in the meander, and there is some yellow there, which is down, maybe 30 dB. I mean, there is some current going there on yours. On the HFSS, I'm not sure what their scale is on those arrows. It seems like there's very, very little current up on it. Okay. And I guess that is current. They're showing direction or something there on the HFSS, and you're showing magnitude, but it just seems like, why would they have all that metal there if it's not being used? So it seems like they could have saved some copper cost,
Yeah, I didn't think about that or really look into it. I just kind of followed their design.
The only other question I have is, you said method of moments, but did you try, especially with the arrays, did you try the MLFMM option in the method of moments under solver settings that would make it go faster?
There was a default solver setting that, like, when I looked up tutorials, it was like, use this for arrays. But whenever you do a patch array, then you should use a method of moments. I'm not sure.
Well, there's a setting in the solver settings called MLFMM. That's that thing we talked about, that it looks to see if things are so far away that it just sets the interaction to 0. And it might be that could have made it run a little faster, because you said it took long. Like when you say it took long, what kind of timing are you talking about?
The first time I simulated the 8-element array, it took 13 hours to get to like
13 hours. That's way too. Yeah. Anytime it takes that kind of time, I try to find something else to do.
Right.
Yeah. But anyway, yeah, you might have been able to reduce that with the MLFMM, just for anybody else listening too. It's taken a long time. I don't know if it would have worked with this, because I don't know what we'd have to look and see what the wavelengths were, but I would bet that it would have reduced the time quite a bit for your arrays.
Mm-hmm.
Yeah. Anybody else have any comments or questions? We should move on here. We probably, when we actually get 3 in a day, we'll probably have to, reduce the length of the questions. But very, very good and very interesting, and very good job on bringing us up on 5G. That's great.